In computer science, confluence is a property of a rewriting system describing which terms in such a system can be rewritten in more than one way to yield the same result. This notion is inspired from the geography, and it has the meaning that the meeting of two bodies of the water. So, and in a similar way, when they have their rewriting systems, and they have some terms, and some terms of these systems can confluence into one term. Okay. Here we have some example. We have this expression, and you can see that they can evaluate this expression in two ways. We can either proceed at first on this left part, or at first this right part. But anyway, at the final point, we will go to the same number. So actually here they have this number can be represented with the different expressions. But when they evaluate them, they all confluent into one number. And if arithmetic expressions evaluate to the same result regardless of the reduction strategy, so here they used two different strategies, but they go into the same result. And if the rewriting system always confluence into the same result regardless of the reduction strategy, this system is said to be ground confluent. If the rewriting system is confluent and also it is terminating, this means that there exists some method to prove the equality between two expressions or terms, S and T. So, because they confluent, at some point we will go into one point, into one term. And because they terminating, so we will go into this point and do some countable number of steps, into a finite number of steps. This means that we can provide some equational theory for such a system. This means that we always can say which term is equal to other terms and so on. So we just take two terms and confluence them with the finite number of steps into one point. And at this point we look that these terms reduction terms are literally agree, and in this moment they say that they are equal. We can express the rewriting system as a directed graph. So at vertices we have some terms, and by arrows they show the actually rewriting. So for example, here we can rewrite A with B, A with C, and if this rewriting system is confluent, then it at this point go to D. And so we can use arrow notation here, which shows that A, for example, A to B, this means that A reduced to B. And if there is a path between two graph nodes C and D, when it forms a reduction sequence. So for instance, if we can have this path from C to D, this long path. When they can express it with, we can just write in such a way. C reduced to D, but here we have this arrow and have this star above this arrow. And it's just indicate that exists a reduction sequence of this path from C to D. And formally, this thing, arrow with a star, is expressed as a reflexive transitive closure of relation, just arrow relation. For example, when they have this example here, the expression, arithmetic expression, they have this reductions path, and actually this path, existence of this path, say to us that there exists a relation arrow star from this term to this term. And now we can define the confluence in such a way that if they have some A which belongs to S, is deemed confluent if for every pairs B and C such that A is if there exists a path from A to B and there exists path from A to C, then there always exists such a D, which for which there exists path from B to this D and C to this D, and they denote this as a B down arrow C. Okay. And if for every term of C is confluent by our previous definition, when they say that the arrow itself is confluent, so reduction itself is confluent, if for every term it is confluent. And this property is sometimes called the diamond property. And so by the intuition it means that just if they have some element, some term, and from this term, if we take absolutely any 2 points, and there exist such paths to these points, then for these 2 points there exists 1 point to this, it will confluent. Okay. There is also exist a notion of local confluence. It defined in such a way if they have some element A and is said to be locally or weakly confluent if for all B and C with A arrow B and A arrow C, there exists D with B arrow star D and C arrow star D. Okay. So, and if every A is locally confluent, then they say the arrow itself is locally or weakly confluent, or having the weak Church-Rosser property. As you see, this is the very same with just the confluence definition, but a difference is that B and C here, this B and here this C must be reduced from A into only one step, okay? And if they reduced into only one step, then there must exist a path from B and C which reduce from one step from this A, and from this B to C there exists some path, this go, and goes into some D. Interesting that the system can be locally confluent, but not globally confluent. You can see this example here on a picture number 3. And let's see that this property of the local confluence is violated here. To satisfy this constraint of the local confluence, every point here must be weakly confluent. What does this mean? This here by definition they see that for all B and C's with A follows B and A follows C, there exists some D with path from B to D and C to D. Here, let's look at all of them. If we look at the A, so we can see that there is no such B and C's, and that's why it's okay, satisfy. If we look at B, we can see that we can, for example, go from B to A, and we can go from B to C. Okay, they have one this pair, but we can from A we can go to A again, and from C they can go to B and A, and we confluence do the confluence into one point. Okay, B is satisfied. Not B not satisfied, because now we can also but not yes, B is satisfied. In the term of local confluence, B is satisfied. But in the term of global confluence, we have the A arrow star here and arrow star here. This means that they must to review also the path from B to C and C to D. And now, if we look at the second path as a B to A, what we have? We must have some path from A to some point and from D to this point. So we also must confluence. But here they can see from D we can't go anywhere. And from A we can go to only to A. This means from these two final points B and A and B, C, D, we can't confluent. We can't confluent anywhere from A and from D. This means that global confluence is not satisfied here, and that's why it is local confluent but not global confluent. And here we have one more example of the infinite non-cyclic local confluent but not globally confluent rewriting system. We can see this thing by why it is satisfy the local confluent property, because if we take every one arrow path, for example this and this, we can see that it confluent into this point, for example, and so on. If they take, for example, B, we have this path, one path, and this one path, and they confluent to this. If we take C, they have this path and this path, and they also confluent. D and E, they also have the confluence, and E and for example, if we take E, we have these and these, and these paths also confluent, and so on. But the global confluent property doesn't hold here. For example, for A, if we take this A, we have this path and this path. And from these 2 points, there is no confluence. there is no confluence along W1 and W2. Church-Rosser property. A rewriting system is said to process the Church-Rosser property if and only if x is equivalent with a star y implies that x and y have the confluence for all objects x and y. So in other words, if we pick up two objects x and y, and if for them holds this relation, so this means that they have some path from x to y and from y to x. If this holds, then this must imply that x and y have the confluence. So in other words, this means that there exists some d for this x and y. For this d must be a path from x to d and from y to d. So we go into one point. And Church and Rosser proved this for lambda calculus, that it has this property. The notions of the semi-confluence. This definition differs from a local confluence. And the constraints look like this. So if they have some, if they pick up some point in our system or some term, and they have some, for this point we have some arrows from A to B and A star to C. So this must, from these two relations must follow that exist D, which can be achieved from B with arrow star and from C with arrow star. And if every A is semi-confluent, we say that the relation itself is semi-confluent. Semi-confluent element need not be confluent, but a semi-confluent rewriting system is necessarily confluent, and a confluent system is trivially semi-confluent. And a strong confluence. Strong confluence is an operation on local confluence that allows us to conclude that a rewriting system is globally confluent. Okay. So the element is said to be strongly confluent if if they have some arrow from A to B and A to C, there must exist D with which can be achieved from B with some path to D, and if the C D must follow C, and or D must be equal to C. So if every point or term is strongly confluent, we say that relation arrow itself strongly confluent. A confluent element need not be strongly confluent, but a strongly confluent rewriting system is a necessarily confluent.